We are currently scanning billions of star systems for any trace of biology. It's an investigation conducted through the dust and debris of the cosmos. For decades, the search has relied on a single premise, that life is identified by its individual components, specifically building block molecules like amino acids. NASA has spent billions of dollars on robotic missions designed to detect these specific molecular signatures on the surfaces of other worlds. However, recent data suggests this strategy is vulnerable to a specific kind of cosmic interference. Molecules once thought to be exclusive to biology actually form spontaneously on dead space rocks, drifting through the vacuum without any living process involved. Meteorites recovered on Earth contain high concentrations of these organic compounds, despite originating from entirely lifeless environments. Laboratory experiments have successfully replicated this, synthesizing both amino and fatty acids in simulated space vacuums using only heat and radiation. Because the basic ingredients of life can exist without a biological source, simply finding these molecules is no longer sufficient to confirm a discovery. To solve this, researchers began looking past individual molecules to study the broader structure of macroscopic ecosystems. On Earth, ecologists assess the health of a forest by analyzing its biodiversity, the variety and distribution of its inhabitants. This analysis relies on richness, the total number of different species present, and evenness, the balance of their distribution across the environment. Scientists applied this same mathematical logic to the molecular level, looking for these patterns within microscopic samples. Confirming a biological presence now depends on identifying a specific structural organization within a chemical sample. The team analyzed over 100 existing datasets, comparing the chemistry of microbes in soil against that of meteorites and laboratory-made samples. This scatter plot shows how amino acids are distributed. Biological samples consistently form a varied and highly uniform mathematical pattern. Non-living chemistry looks entirely different. It produces erratic, uneven distributions, where some molecules are overrepresented and others are missing entirely. Fatty acids showed a mirrored but equally distinct trend. Living systems impose a specific, predictable order on their chemical environment. Biological activity leaves a permanent mathematical signature in the statistical organization of these molecules. On other worlds, evidence of life would likely be millions of years old and heavily degraded by radiation. To see if their method could withstand these conditions, researchers tested the framework against ancient biological samples found on Earth. They applied the math to fossilized dinosaur eggs to determine if the biological pattern could survive the process of fossilization. Even in these stony remains, the statistical signature was detectable. The math even revealed the precise level of biological decay. This statistical signature is resilient enough to identify biological activity long after the organisms themselves have vanished. This discovery is based entirely on statistical analysis, which eliminates the need to develop expensive new sensors. This statistical framework can be applied immediately to the massive archives of chemical data already gathered by space missions. We can now re-examine data from Jupiter's moon Europa, looking for these patterns within its icy surface and subsurface ocean. The same method applies to the organic molecules detected within the water vapor plumes of Saturn's moon Enceladus. Evidence of biological activity may already exist within the terabytes of raw data stored on our own servers. No single statistical result will ever be sufficient to declare the discovery of life. Future claims will require multiple independent lines of evidence, cross-referenced with the geological context of the environment. However, when multiple analytical techniques detect these specific statistical fingerprints, the case for extraterrestrial life becomes increasingly difficult to ignore. Identifying these organizational patterns allows us to recognize life even when its chemistry differs from our own. Subscribe for more cosmic mysteries.